Have you ever stopped to think about how we can be so sure that a kilogram here is the exact same as a kilogram on the other side of the planet? Well, today we're diving headfirst into that very question. Welcome to our quest for the perfect measurement.
No, really, think about it for a second. How does a scientist in Tokyo know that the gram they're measuring is exactly the same as a gram being measured by a scientist in Argentina? It sounds almost impossible, right? But the solution is actually this beautiful mix of simple and super complex all at the same time.
And hey, welcome to Learn with Ease. This is the spot where we take all the tricky parts of physics and make them simple and clear, helping you build your understanding all the way from the basics to total mastery. And today, we are definitely on a quest for that perfect measurement.
So, every good quest needs a starting point. And for us, it starts with language. I mean, before you can measure anything, you've got to make sure everyone's speaking the same language, right? In science, that common language is built on a set of standard units everyone agrees on.
This is where something called the International System of Units, or just SI units, comes into play. You could think of these as the rock-solid ground rules for all of science. They are the 7 fundamental building blocks that pretty much every other measurement is constructed from.
And here they are, the magnificent 7. You've got the second for time, the meter for length, the kilogram for mass, and a few others. This table, it's basically the alphabet for the language of science. With just these 7 units, we can describe and measure almost anything in the entire universe. How cool is that?
Okay, so we've got our language down. Now we need the right tools for the job. Because let's be honest, any measurement you take is only going to be as good as the instrument you're using to take it.
All right, first things first, let's clear up a super common mix-up. Mass is not the same thing as weight. Mass is the actual amount of stuff that makes you up, and that number never ever changes no matter where you go. Weight, on the other hand, is just the force of gravity pulling down on all that stuff. That's why your mass would be the same on Earth as it is on the Moon, but you'd weigh a whole lot less on the Moon. And understanding that difference is key because it means we need different tools for the job.
So what's the difference in the tools? Well, a classic balance scale, the kind you see in old science labs, literally measures mass. It works by comparing your object to another object with a known mass. It's super precise. Your bathroom scale, though? That's an electronic scale, and it's actually measuring weight. It uses a sensor to see how much force gravity is exerting. It's fast and easy, but it's measuring a force, not the fundamental amount of matter.
So, with that in mind, let's say you're in a lab working on a really sensitive experiment. Which tool are you going to reach for? Yeah, you got it. You're going to want the one that measures mass directly and with the highest precision, the balance beam.
But what if we need to get even smaller, like way smaller? What if you needed to measure something impossibly thin, like a strand of hair or a piece of paper? For that, you need a specialized tool, like this, the micrometer screw gauge. This incredible piece of engineering can measure things with an accuracy of 1/100th of a millimeter. Just wild.
And I know it looks a little intimidating, but using it is actually pretty straightforward. You just place your object in the clamp, gently tighten it with the little ratchet at the end that makes sure you don't crush it, and then you just add the reading from the main scale to the reading on the circular scale. It's all about taking careful, consistent steps.
All right, we have our language and we have our tools, but what actually makes a measurement a good one? To answer that, we need to get into 2 really important ideas, accuracy and precision. Now, these 2 words, accuracy and precision, sound similar, but in science they mean totally different things. Accuracy is all about being correct, how close you are to the real, true value. Think of it as hitting the bullseye on a target. Precision, on the other hand, is all about being consistent, how close your repeated measurements are to each other. That's like getting a tight grouping of shots.
Let's stick with that target analogy. Picture this. You shoot a bunch of arrows, and they're kind of scattered all over the target. But the average position of all those arrows is right in the center, on the bullseye. That means you've got high accuracy, but low precision. You're right on average, but your individual shots are a bit wild.
Okay, now imagine this scenario. You shoot again, and this time all your arrows land in a tiny, tight little group. Wow, that's amazing precision, right? But that little group is way over in the top left corner, nowhere near the bullseye. So you're highly precise, but you're not accurate. You're being consistently wrong.
And finally, this. This is the dream. A super tight cluster of arrows, all landing smack dab in the middle of the bullseye. That's what we're all aiming for, high accuracy and high precision. This is the absolute goal of any good measurement in science.
But here's a little secret from the world of science. In reality, no measurement is ever 100% perfect. And you know what? That's totally okay. Science knows this, and it has a really smart way of dealing with it.
You see, every experiment is going to have some errors. There are systematic errors which affect your accuracy, like if your scale wasn't set to 0 before you started. Every single measurement will be off by that same amount. Then there are random errors which affect your precision. These are tiny, unpredictable things, like a little bit of electronic static that cause your results to scatter just a bit.
So because scientists know these errors exist, they embrace this imperfection by always stating an uncertainty with their measurement. Now this is so important. Uncertainty is not admitting you made a mistake. It's an honest, upfront way of saying, here's the range where we're confident the true value actually is. It's a huge part of being a good scientist.
For instance, if you see a temperature written like this, it doesn't mean the reading is wrong. It means the measured value was 20 degrees Celsius, and the scientist is very confident that the real, actual temperature is somewhere between 18 and 22 degrees. It's a statement of confidence, not a mistake.
And that brings us to a really deep, kind of mind-bending final question. If every single measurement we can possibly take has some amount of error, some level of uncertainty, can we ever truly know the absolute, perfect, true value of anything? It's definitely something to chew on.
Hey, thank you so much for coming along on this quest for the perfect measurement. We really hope this made things a bit clearer for you. If you found it helpful, we'd love it if you'd hit the like button, leave a comment, and maybe share it with a friend. And of course, don't forget to subscribe and follow Learn with Ease so you don't miss our next dive into the amazing world of physics. We'll see you then.